Good morning, students. Today is Deepavali day. Wish you happy Diwali to all. Let us continue our class, that is synchronous motors. From previous few classes, we have discussed synchronous motor construction, basic principle of operation, its salient points and its significances in industrials and different important applications areas. Now, time came to know that its performance based on well known few equations. Today class we are going to mathematical analysis of synchronous motor. This synchronous motor, as you know, that is a different in construction point of view with DC machines and induction machines motors, whether it is a squirrel cage and slip ring motor. But it is a very significant applications in various important areas. Let us do. Now, let us introduce myself. Myself, Dr. C.H. Yadaya, Senior Lecturer in Electrical and Electronics Engineering, Government Polytechnic, Husnabad. Today topic regarding to 5th semester AC machines, AC motors. Let us recall what we have seen last class. In the previous period, we have discussed about principle of operation of synchronous motor, method of starting synchronous motor and its characteristics of synchronous motors we have seen. Now, in this class, we are going to learn the performance of synchronous motor on no load, assuming no losses, ideal condition. And second case, performance of synchronous motor under no load condition with practical considering losses, few losses, no load losses. And third case, synchronous motor on load conditions. And finally, we are going to calculate analysis of phasor diagram and simple few problems we are going to solve in this class. Let us do one by one slowly. As we know that the synchronous motor behavior on load. So, this before going to our synchronous motor, we well known motors are DC motors. So, from DC motors we will start. When load is increased on DC motor, the speed of the motor reduces. In laboratory, you have performed load test on shunt motor, while one under no load condition, the DC motor runs at nearly 1440 rpm, but the synchronous speed is 1500 rpm. Due to the frictional and windage losses, the rotor runs at nearly 450 rpm. Let us assume. Once the load 1 kg is added by spring balance in our laboratory. We can observe the speed with the help of tachometer. The speed is reduced from 1440 to 1420 rpm. Now add some more load. For example, 3 kgs. S1 and S2 increased. Then you can observe the sound also. The speed of the motor reduces, and we check it with our tachometer. Then speed comes to 1400 rpm only. If further increased 5 kgs, the speed may reduce to the 1350 rpm. Further increase the load, then it will go to the 1200 rpm. That means here, if load is increased gradually, step by step on DC motor, we have observed that the speed is gradually reduced. But in our synchronous motor, if load is increased gradually up to some extent, the speed is constant. That is the main significance of synchronous motor. In DC motors, you can observe armature develops an EMF which opposes the supply voltage. V is called back EMF. So when rotor picks up its rotation, then there is a back EMF developed in the armature. This induced back EMF always opposes the supply voltage. Due to this one, the applied voltage V minus the induced voltage EB will give the resultant voltage across the armature. That is equal to IA into RA. That means this back EMF, as we know that, depend upon the speed. And what is the formula? The EB is equal 5ZN by 60 into P by A. Here EB is directly proportional to the speed of the rotor. So based on this one, we are going to analysis. The resultant voltage across the terminal is equal to applied voltage minus this generated voltage, which is opposed the cause of its production as per the Lenz's law. That is a V minus EB, that is the resultant voltage across the armature. As we know that it causes an armature current given by the expression that is equal to IA RA is equal to V minus EB. So I want the armature current. That armature current IA is equal to V minus EB by RA. As we know that the armature resistance of a DC motor always less than 1. So that's why we require some starters. Okay, that is already known. Where RA is the armature resistance. Now the back EMF is equal to EB is equal to 5ZN by 60 into P by A, where is a 5 is the flux, Z is the number of conductors, N is the speed in RPM, and 60 and P is the number of poles, A is the number of parallel paths. The back EMF in a DC motor depends on armature speed. In synchronous motor, the back EMF is set up in the stator itself due to the field injected into rotor circuit. Here whatever the DC supply is given to the rotor through the slip rings, that due to this one, it induces a voltage in the stator. That voltage is opposed to the applied 3-phase supply input voltage. Here we are controlling stator input 3-phase AC voltage with help of our DC supply. So, why? Because we are generating the back EMF. Armature is EMF is generated, that is a back EMF, that is always opposite the applied voltage, that is called 3-phase applied voltage is opposite by the back EMF developed in the stator due to the field in rotor circuit. That is the difference in synchronous motor. The back EMF depends on excitation given to the rotor field only. It does not depend on speed similar to the DC motor. In DC motor, the back EMF depends on the speed, but in this case the speed is constant. Then it depends only on excitation on rotor, whether you are going to normal excitation, over excitation, under excitation. What do you mean with this excitation? So we will see later. That is injecting the DC supply to the rotor. So based on this voltage injected into rotor, so we are going to produce back EMF in stator that dictates the current drawn from supply to armature winding of stator. Okay. Now you can see in synchronous motors is different. In case of DC motors, so what we have seen, so in DC motors here, in DC motors, so what is happened? So here a armature, this armature due to this one, it will be goes the speed. The speed is developed initially, back EMF is equal 0. Once rotor picks up its speed, then EB increases and the back EMF is directly proportional to the speed in DC machines. But whereas in our synchronous machine, so EB is directly proportional to excitation current, that is equal to the flux developed in rotor circuit, that is equal directly proportional to the field current in rotor. Okay. So this is a difference from DC motors. Now let us see. The similar to the DC motor, armature current for a synchronous motor is given by armature current for phase is equal to, so V is the applied voltage and EB is the back EMF developed in the stator by ZS is the synchronous impedance and IA is the armature current. Let us here you can see it. Okay, now you can see it. Here is this is equal to the stator. This is equal to the rotor equivalent. Now here EB back EMF, EB is generated in stator due to rotor DC supply. Okay. Now here is applied voltage is equal to V and current drawing from the armature is equal to IA and it has a winding in 3 phase, and for phase we are going to calculate, that is R plus J of X, inductance plus resistance, that is equal impedance value. Now what you have seen, now in this case, So this is the applied voltage V, and here developed voltage is the EB. The current is passing for phase is equal to armature current IA. So based on this one, and the winding each has the impedance of Z, synchronous impedance. Now based on this one, in stator we are going to write the equation. What is the applied voltage? V, input voltage minus induced voltage, that is the KID, EB, by this is the difference of voltage, applied voltage minus EB divided by, what is the value here? So current, the or we can write it. So what is the drop voltage? That is equal to IA Z. That is the equation. So we can write it this equation separately. What is the equation? So here we applied voltage, you can see here the applied voltage, whatever the applied voltage V is equal to drop, that is equal to IA ZA plus induced voltage, this EB. So here the voltage, this is equal to, you can see this, what are the voltage here, then applied voltage is V, is a current is passing through the IA. So IA and ZA, this is the drop, and here is the EB. So based on the simple circuit, applied voltage, this voltage is equal to, it will meet across here, across here. So this is a simple equation. Now analysis. Now armature current for phase is equal to IA is equal to V minus EB by ZS, where ZS is the RA plus armature resistance plus J of synchronous reactance or impedance, you can say the reactance XL. Now RA is the stator resistance for phase, X is the synchronous reactance for phase, and V is the applied voltage for phase, and EB is the back EMF induced in the stator. Now synchronous motor on no load conditions. Now with terminology we have learnt. Now motor is started by using the external motor. Three-phase supply is given to our motor. It rotating, it produced a rotating magnetic field in the stator. Now we have given some external motor connected to our rotor and rotated near to the synchronous speed. Then we given the DC supply to the rotor. Then stator field and rotor field interlocked each other. The motor is running. Now remove the input motor which is connected to our rotor. Now our motor is under running condition. We are not loaded on shaft. Now let us assume we ideal condition, the very good condition, there is no losses. When the motor is running on no load with field excitation, it is assumed as no losses. That means no friction and windage losses, no iron losses, no copper losses. Let us assume the magnetic locking between stator and rotor is such a way that the magnetic axis of both coincide with each other as shown in the figure. What is the figure? You can see here. Here, under normal condition, stator magnetic axis and rotor magnetic axis both are coincides. The angle difference between the two axes are 0. Here, north pole of stator and south pole of rotor coincides, interlocked at both A and B. So, at A and B axis, stator axis and rotor axis coincides, and there is no difference between the axis. In this case, first let us assume what will happen. Now, when during this condition, whatever the EMF induced in the stator, that is back EMF, is the magnitude is equal but 180 degrees opposite. That is the opposite the applied voltage. Then V is equal to EB. Then, so what is the formula? We have seen IA is equal to V minus EB by ZS. Here you can see. So, V minus EB by this value, difference value. In this case, this applied voltage is equal to induced voltage, but in opposite direction. The difference of this voltage becomes to 0. Now, what is the armature current? Here armature current IA is equal to 0 by ZS, synchronous impedance, that is what 0. That means the current drawn from the supply is equal to 0. But our motor is running. The current is 0 if you are seeing ammeter. But is it possible? So, here mechanical energy is generated with the help of the electrical energy. What is the input energy? Electrical input energy to our motor. Our input energy to our motor is equal to applied voltage, that is the input voltage is equal to, we require the some voltage into current, that is equal to, so in 3 phase root 3 VL IL cos phi. So, root 3 VL 400 volts in 3 phase we are applied, IL line current or phase current. Now, the current becomes to 0 in this case. 0 into something, 0, input power is itself 0 in mathematical. So, there is no input, but our motor is generating mechanical energy output, but we are not added any load, but our rotor is rotating. At the same time, there is a friction and windage losses, some mechanical losses, some iron losses, some copper losses. Everything is running, everything is coming, but it's showing armature current is 0. Input current itself 0, but how the mechanical energy is generated? So, in ideal condition, theoretically it is not possible. So, what to do? The both the vector difference V and EB is 0 and hence current is 0. Normal excitation. The motor takes no power as there is neither load nor losses, but in practice this is impossible. Motor has to supply some mechanical and iron losses along with the small copper losses during production of mechanical energy. It is happening, but current is showing the 0. So, this is purely theoretical, but it is not practical. Let us see in practical. We are assuming, in previous case we are assuming no losses in the motor under no load condition. Now, in this case it is not possible in practically, but in this case the same no load condition on motor considering few losses. This is a few losses we are considering. Then let us analyze this system once again. When synchronous motor is running on no load with losses, the magnetic locking exists between the stator and rotor. Still, stator and rotor axes are interlocked each other, but there exists a small angle of difference between the two axes of magnetic field as shown in the figure. In this case, stator magnetic fields along the A and B axis only, but we are assuming that due to this inherent losses, the rotor is retarded some angle by some alpha. So, we can see this is a load angle. Some lagged, it is a some alpha. Now, the rotor, you can see in the figure, red color is a stator magnetic field and blue color is a rotor magnetic field. In between there is a angle. The first case you can see here, when in this case both are coincides, but it is not practicably. Now, in this case we are assuming small losses, inherent losses. At that condition, this is a stator magnetic field axis across A and B. Now, the rotor axis is, this is a blue one. Now, it is a twisted in anti-clockwise direction, some angle. So, this angle we say is alpha. Now, you can see the figure also. What will happen by changing some difference between the two magnetic axes? So, then see, the rotor axis falls back with respect to stator by an angle as alpha as shown in the figure. This angle alpha decides the amount of current required to produce the torque to supply to meet various losses. That means the alpha decides how much armature current has to drawn from supply to meet, to develop torque to meet this inherent losses, some small amount of the copper losses, iron losses and friction and windage losses. So, that is equal to, hence the angle alpha is called load angle, or we can say the power angle, or we can say coupling angle, or we can say angle of retardation. Alpha we can say the load angle or power angle or coupling angle or angle of retardation, whatever the you assume it. Alpha is created between the stator magnetic field and rotor magnetic field. Now, you can see draw the figures. In this case, though magnetically the magnitude EB is equal to V, EB will not be located in exact opposition with V. Now, you can see, please see the vector diagram. Vector diagram is a very important, and if you are understood the vector diagram, everything is very easy. So, please see it. Here what is happened? In previous case, V, this one applied voltage, and whatever the induced voltage EB. Okay. So, magnitude is equal, but angle is the 180 degrees opposite in ideal condition. Now, due to the some losses, this EB, whatever the EB here, whatever the EB, it is raised to some angle here. So, both are opposite direction, there is no meeting here. So, here is some compromisation takes place. Now, it is from this angle to this angle is raised, some alpha raised, there is some head, some alpha angle raised in clockwise direction by EB. Now, you can see what is happened. So, both are some, there is a resultant value. Here EB, this is a EB, and here is a V resultant value. Previous cases, what will happen? So, here this person facing south direction, this person facing south direction. What is the understanding between these two persons is the opposite. There is no discussion between the two persons dispute. We want to solve the disputes between this V fellow and EB fellow, but both are equal powers but in opposite direction, south and north. There is no compromise between the EB and V. No talks between EB and V. Now in this case, now EB is compromised somewhat. Now in this case what will happen? So alpha angle is raised. Then if one person compromised to some level, then is a problem may be solved. Similarly you can see here, though, so the displaced from its initial position by angle alpha as shown in the figure, that is a load angle and coupling angle. In this case we know that two vectors V vector, AB vectors. So vectorially we can sum it. So ER is a resultant voltage. As we know formula, that is equal to, so ER square is equal to V square plus EB square minus 2 into EB into V into cos alpha, that is the angle between the two voltages. Well known formula. Apply that one, we are going to get, so this ER. So this vector we know, this vector we know, based on the formulas, this whole square plus this whole square plus minus 2 into this into this into something, we are going to get the formula. Then we are going to get the ER. So resultant voltage induced in the rotor. So in formula what will happen? So here IA is equal to and V minus EB by ZA or ZS, synchronous impedance. Now in this case it is not equal to 0 value, some value, that we can say ER. Okay. Now what is the formula now? Now we can write it, IA is equal to ER resultant voltage by ZS. So resultant voltage, so IA ZS is equal ER. Once we know the ER, there is a possible to generate the back EMF. So already back EMF is generated. So if this current, now this current is present in the system, this current is enough to generate the some torque which is to meet the these losses. Now see, hence the vector difference between EB and V is not 0, but gives rise to a resultant phasor ER as shown in the figure. But V minus EB is equal IA plus ZS is equal ER. This resultant decides the amount of current IA to be drawn to produce the torque to meet these few losses under no load conditions. Now you can see here the vector also you should know. Now what happened? So in this case here this is a ER. Now vectors you can see here. So this is a applied voltage, sorry, okay, this is a applied voltage and this is a induced voltage. This is a voltage applied, correspondingly some current is drawing here, IA, the phase angle, that is a phi, power factor angle, IA and V. Now resultant we are going to get this ER, that is ER. Now the angle from ER to IA, armature current, is the, we can say the theta. Now the angle here is alpha. So alpha is a load angle, where theta is the internal angle. We can say that is the internal angle. Here phi is the angle between the applied voltage, armature current, that is the power factor angle, whereas the theta is equal to internal angle, is a angle between the ER resultant voltage and armature current, and alpha is the EB versus and this angle. So, these angles you should remember. Now, so armature current IA is equal to ER by ZS. Under no load condition, alpha is very small. So, only small amount of the retard takes place with respect to the stator flux. Hence, ER is very small, the difference voltage is very, very small. The current drawn by the motor is very small, then current also very, very small amount of the current will draw to meet these inherent losses. As the load on the synchronous motor increases, the load alpha increases, but there is no change in the speed. What we have seen, as the load on the synchronous motor increases, the load angle alpha increases. If you are going to add the load on rotor, the alpha value increases. That means the EB, the axis of the rotor axis, some more retards. It comes to the towards the anti-clockwise direction. Alpha increases, but the speed will maintain constant only because both are connected magnetically. As alpha increases, the resultant voltage ER also increases. We have seen that if resultant voltage depend upon the alpha, if alpha increased, the difference voltage increases. The current drawn by the motor also increases. You can see in the figure. If alpha increase further, then what will happen? So, ER value also increased, then armature current also increased. So, the alpha, when alpha is increased, when load on motor increased. This current produces the necessary torque which satisfies the increased load demand. Hence, it maintains the constant speed. The magnetic locking still exists between the stator and rotor axis. The synchronous motor on load, let us assume the angle alpha goes on increasing as load increases. Now, the angle alpha goes on increased as load increases. Let us analyze this one. Now, in the first case, you can see here, in the first case, alpha value is less. Here, the load increased on the motor, the alpha increased further. If further load increased, then alpha becomes to nearly this angle 90 degrees. So, this is a maximum. If further increases load on rotor, that means this axis and this axis go on coming this direction. Now, in this case, the axis, this one, this axis here. So, here is a 90 degrees. The maximum developed, that EB minus V minus EB is a maximum, ER is a maximum. If further increased, then automatically, so in this case also, that is the this stator and rotor axis somewhat is coming here. So, this axis is nearly 90 degrees. Even then both are coupled. If further increased on the load on rotor, then it will comes this direction and there is a break between the stator and rotor magnetic coupling. Then motor will come out from magnetic coupling and comes to standstill position. That means we can change from this place to this place to this place up to some extent. Here you can observe, this is a stator. Now you can observe, here is the stator. Initially, this is a rotor. Coincide, both axes are coincides. No losses we have seen. Now, in second case, we are assumed just here is a changes. So, this axis and this axis, and between this is a coupling angle alpha raised. Rotor is moved some extent here. Now, further if load added, then automatically, so this axis is one, and now the rotor, so this rotor axis comes this direction. Then alpha increased further, and even if I increased further up to 90 degrees, then this angle and this angle is a alpha is a 90 degrees. In this is a lost position, then even then it is a magnetically coupled, it will run at the same speed of synchronous speed. Then at that condition, what will happen? Maximum ER is developed, and maximum current is drawn from the supply to develop the torque. This torque is meet the increased load on rotor to maintain constant speed of synchronous speed. If further increases, what will happen? If further increases, now here, then it will comes out of direction. So, this is a north pole, this is a south pole of the rotor, and comes this alpha is above the 90 degrees, and the coupling between the magnetic coupling between the stator and rotor breaks. Then rotor comes to standstill position. So, this is a vector diagram, similar this vector diagram. Now, you can see the maximum possible limit of alpha is 90 degrees electrical. If alpha is increased beyond 90 degrees, what will happen? The magnetic locking between stator and rotor axis breaks, and the motor will comes out of synchronism. Then the motor stops. You can see this is one thing. The torque produced at alpha is called 90 degrees maximum. You can see there is a graph between the load angle and torque developed in the motor. The load angle here, you can see same, this is the maximum value 90 degrees. Go on increasing and load on rotor, it will goes on increasing, then alpha also increased up to the 90 degrees, then it produces a maximum. Behind that, you are going to add some more load, then slowly comes to its torque reducing and reducing. At that condition, the torque developed in the motor becomes to 0. That means here you can see this torque is called pull out torque. The torque which is produced at alpha is equal to 90 degrees is known as the pull out torque. If pull out torque is exceeds beyond the 90 degrees, then it will stops to generate any energy to run the motor. And angle of retard or angle of advance, what do you mean by this one? The angle with EB, that's a back EMF phasor, moves from its initial position so as to give a rise to a resultant EMF is called the angle of retard or load angle. So, here we have seen that here is the V and here is the EB. Now, the EB is raising from this angle, raising this too. So, what will happen? Up to raising this is a maximum. This is alpha, this is the alpha. So, this raising, that is the angle with EB phasor moves from its initial position. This is the initial position. It is a moving, it is a moving, it is a moving. So, every time, so here alpha 1, alpha 2, alpha 3 corresponding to the load on motor. So as to give the rise to resultant EMF ER. So that raised angle is known as the angle of retard. Angle of retard is nothing but alpha. Now, angle of advance, what do you mean the angle of this angle, between this angle. So, total is a 180 minus this alpha will give the angle of advance. I think you have the idea. Now, what happened here? This is the normal V, this is the EB. Then alpha is equal 0. Now, second case, EB is raised to the some alpha. Then there is a present ER. And here alpha is angle of retard, whereas this angle is known as the angle of advance. Here 180 minus alpha will give this value. It is known as the angle of advance. Okay. So, these terms comes in problems. So, that is why you have to remember the terminology. What do you mean by the angle of retard and angle of advance? Now, analysis of phasor diagrams. Very familiar phasor, already you known in BW subject and AC circuits and electrical circuits. Now, the analysis, let alpha be the load angle and armature current IA is equal to resultant ER by ZS and resultant EMF ER is equal to, so that is we are going to calculate. So, what is the ER? ER is equal to resultant EMF, that is equal to the vector sum of V and EB, that is equal to root of EB square plus V square minus 2 into V into EB into cos angle between the EB and V. So, we are going to get that formula. Next, synchronous impedance ZS. ZS is equal to armature resistance plus synchronous reactance RA plus J of XS. Then theta is equal to tan inverse of XS by RA, synchronous reactance by armature resistance. This theta is known as the internal angle or impedance angle, we can say. Okay. Now, so this formula already we know. Now, the angle theta is called internal mission angle, or you can say the impedance angle. So, the theta angle between the armature current versus resultant voltage. Phi, the angle between the applied voltage and armature current. Alpha, the angle between the reference value to back EMF, where the theta is the internal mission angle or impedance angle is always constant. So, what is the constant? Tan inverse of X by RA. So, that is the synchronous reactance by resistance. The resistance at the time of manufactured is a constant value, reactance also constant value. So, somewhat XA by RA tan inverse we are going to theta angle, that is constant value. The significance of angle theta is that it tells us armature current lags behind ER. So, this decides whether armature current, the angle between the armature current and resultant voltage, whether it is a leading or lagging. It will give the value. Significance of theta is that it tells us the IA always, that is the armature current always lags the voltage and due to the inductive property, and practically the RA is very small as compared to the reactance value. Let us neglect RA, then rewrite the equations. At that condition, tan inverse of XS by RA is taken as equal to a small value, negligence value. Then what will happen? The theta tends to 90 degrees. That means ER, so ER and armature current is always 90 degrees. if RA becomes negligence, small value, so that is equal excess synchronous impedance very large as compared to the RA. Then the power factor angle phi, angle between the V into IA, and cos phi is equal power factor at which the motor working. So this is the thing we are going to these are the topics we have covered in this class. The continuation of this next class we will see in the next class. So what we have discussed in this class, the basic just performance. So we have discussed in the class about the performance of synchronous motor on no load with considering ideal condition, no losses takes place in the motor while motor is running. So that seems it is not practicable. Then we have considered some few small amount of the losses to meet some torque. Torque is produced drawing a small amount of the armature current. Then we have analysis that situation also. Now we have added some load on the rotor. Then how the alpha is changes. If changes alpha, what is the performance of the system also we have seen. At the same time, we have seen the analysis of phasor diagram also. So these are the some portion of performance of synchronous motor. So we will discuss remaining part in the next class.